Hello and welcome back. Today we introduce the tangent and other trigonometric functions. Note that Project 6 is collected next class, so take a look on the syllabus calendar for the date. After that, there'll be a break between the collecting of Project 6 and the assignment of Project 7. In that break, you will have quiz number 6, required form number 2, as well as a response to somebody else's required form post. That's due class 25. And then test number 2, take a look at the syllabus calendar for the window for you to take test number 2. So let's get started here in the class notes. Number 1, in this section, we extend our definition of tangent and define the other 3 trigonometric functions. We begin by filling in the coordinates of the point x, y in the diagram at right. Okay, so we've seen this diagram a few times. Hopefully we know that the x is r cosine of theta, not just theta. Not just cosine theta, but r cosine theta, and the y is r sine of theta. Those things just become cosine theta and sine theta when you're in the unit circle, because then the r becomes 1. 2, in order to make our new definition for tangent agree with our tangent theta equals opposite over adjacent definition, then we must define tangent as, and then we're going to fill this in. So we remember from SOHCAHTOA when we had a right triangle, we defined tangent of theta to be opposite over adjacent. We want to make sure that we're still defining tangent in that way, but we're going to extend it. So the opposite side is y and the adjacent side is x. So that means the definition of tangent, it better be y over x if it's still going to agree with opposite over adjacent. And the nice thing is that y over x agrees with opposite over adjacent whenever you're in a right triangle. But this angle theta could get bigger than the 90 degrees. It could be anywhere. It could be out here. It's no longer part of a right triangle, but y over x still has meaning, and that's still how we define tangent theta. Number 4, find tangent of 3 pi over 4 using the unit circle. So what you'll need to do is pause the video here, find the unit circle, and then come back. Okay, so hopefully we've got the unit circle in front of us. 3 pi over 4, we got to find that someplace on the unit circle. So which quadrant is 3 pi over 4 in? I'll just draw a mini unit circle over here. So 3 pi over 4 is in the second quadrant. In fact, it's perfectly halfway in the second quadrant, 3 pi over 4. And so you just need to know the coordinates of that point right there. It might be something like negative 1 over root 2 comma 1 over root 2. Or those denominators could be rationalized. It would be negative root 2 over 2 comma positive root 2 over 2. Either way, we're going to take the y and divide it by the x. So let's write tangent 3 pi over 4 here is equal to, and you don't need to write this in general, but I'm just highlighting our new definition. It's y over x. So the y coordinate is positive 1 over root 2. The x coordinate is negative 1 over root 2. When we simplify, we just get negative 1. So the tangent of 3 pi over 4 is negative 1. We'll confirm that on the calculator. So tangent 3, the pi button is right here above that caret, divided by 4. And again, anytime I hit sine, cosine, or tangent, I always make sure that I know what mode I'm in. We should be in radian mode here. We are. You can see it there. So we should get the right answer, which is negative 1. Let's use, all right, so moving on to number 5. Let's use the picture above to find the slope of the line that makes an angle of theta with the positive x-axis. So same picture as we had over here. I'm just asking you to find the slope of this line, the one that makes the angle of theta. So we know that the slope is the change in y over change in x, or rise over run. In this case, the run, let's see, rise over run. So the run is positive x, and the rise is positive y. So rise over run should be y over x. So the slope of that line up there is y over x. But wait a second, we've just seen y over x. This class, we saw it right up here. Y over x is the tangent of theta, but y over x is also the slope of a line that makes angle theta with the positive x-axis. So what that means here in number 6 is that tangent of theta is equal to the slope of the line that makes an angle of theta with the positive x-axis. So it's a really nice way to think about tangent, this new trig function. It's just telling you the slope of the line. If you are sitting at some angle theta, like in that picture in the top right, then tangent of theta is just the slope of that line. Number 7, use the graph to estimate the slope of a line making a 20-degree angle with the positive x-axis, then get a better estimate by using your calculator. Okay, so we've got our line drawn in here. I'm telling you that's a 20-degree angle. I want to know what the slope of this line is. We're just going to estimate the slope by counting boxes. So we're just looking for a point. Let's see, so the origin looks pretty good. That's right on the line. And then we want another point that's a nice point and it's close enough to being on the line. So for example, maybe this point right over here, it's pretty close to being the point 3, 1. It's actually like, I guess it's like 3, maybe 1.1 or 1.2. It's not quite 3, 1, but that's okay. So that means that the slope is the change in y over change in x, 1.1 over 3. And we can estimate that on the calculator. So 1.1 is just my guess divided by 3. And so we get a slope of about 0.367. Okay, but how could we get a better estimate than we just did? Well, we just saw that the slope of that line had better be exactly tangent of some angle. It's tangent of 20 in this case. So if we just type tangent of 20, then we should get exactly, well, at least a very good approximation for the slope of that line. We're hoping it's something around 0.367. So let's see what we get here. Tangent of 20, 2.2. Goodness, that's not close at all. Okay, we broke our cardinal rule here. Whenever we hit sine, cosine, or tangent, we need to think about something on this calculator. That's the mode. And of course, we're in the wrong mode because we did a radian problem just up above. So if we're in degrees, we should get the right answer. So we'll try it again. Tangent of 20. Still hoping it's going to be something near this 0.367 that we got. And that's pretty darn near, 0.364-ish. So we just saw that tangent of 20 is roughly 0.364 from the calculator. And that's a better estimate for the slope of the line. We were pretty close with our guess. 8, here's another way to think about tangent theta. What can we say about the value of sine theta over cosine theta? Well, let's go ahead and fill this in. We know that sine theta from our x, y, and r definition is y divided by r. We know that cosine theta is x divided by r. Pause the video here, do some algebra, and clean up that complex fraction and come back when you're done. So hopefully we did some work and got y divided by x. Oh, lo and behold, y over x again. So what does that mean? It means that tangent of theta is exactly the same as sine theta over cosine theta, because they're all equal to y over x. 9, thus we have several different ways to think about tangent of theta. Our definition was tangent theta equals y over x. It agrees with our definition, tangent theta equals opposite over adjacent. We've just seen that tangent of theta is sine theta over cosine theta, and then up above we saw that tangent theta was the slope of the line that makes an angle theta with the positive x-axis. So tangent is all of those things, and you can think about any of them. Next page. Let's use our unit circle to try to sketch the graph of y equals tan theta on the interval negative 90 degrees to 90 degrees. Okay, so let's give this a shot. So here's 90 degrees, and here's negative 90 degrees. And the first thing we're going to do is plot some points. So let's make a table here. So we're going to have theta, and then we're going to have tangent theta. And we'll plot a few points. How about we plot, let's start by plotting 60 degrees, and then 45, and then 30, and then 0 degrees, and then we'll do the negatives of these guys. Okay, so using the unit circle, we've actually already done one of these. Well, kind of. Well, let's just start over. So we've got our unit circle in front of us. If we don't, we should pause the video and go grab that unit circle. We're going to get it again. So tangent of 60 find the 60-degree angle on your unit circle, and we know that tangent is really y divided by x. So what is the y for that 60-degree angle? And divided by whatever the x is for that 60-degree angle. Okay, so the y is root 3 over 2, and the x is divided by, and then the x is 1 over root 2. And when we simplify those, radical 2's, something is funny here. Maybe I should write it in this way, root 2 over 2. That's a better way to write it, so that then we can, no, something is not right. Root 3 over 2 is that one. Silliness. 1/2 is this one. That's what happens when you try to use the unit circle and it's not in front of you. Silly mistakes. So the 2's cancel here, and we just get root 3 over 1 or root 3, which you can type on the calculator. You'll see is about 1.7. For 45 degrees, again, we're doing the y over the x, so look at your unit circle. And for 45 degrees, you should see that the y value is root 2 over 2, and the x value, I'll do this in a different color. The x value is the same. It's root 2 over 2 divided by root 2 over 2, which is simply 1. Next one is 30 degrees. Here the y value is 1/2 divided by the x value, root 3 over 2. And again, we cancel those 2's, and we get 1 divided by root 3, which I don't happen to know off the top of my head, so we'll get an estimate on the calculator. So 1 divided by second square root of 3, and we get 0.58. One thing you might do just to double check, make sure that everything is hunky-dory, is actually just type in tangent of 30 degrees. I think we're still in degree mode, but let's just double check. That's fine. And so we should get the same thing. 5758, we'll say. Okay, and then for the 0-degree angle, you're still doing the y and dividing by the x. And the y in this case is 0, and the x is 1, and so all told that is 0. And you swing down into the 4th quadrant, and you handle the negative 30, negative 45, and negative 60. So pause the video, see if you can write down the same kind of fraction over fraction, and then reduce and get some radical maybe, and then get a decimal. Come back once you've filled in the rest of this table. Okay, so hopefully we discovered that it's the same exact numbers as up above, but they're all negative. And so then we can sit here and plot a few points. So let's go ahead and mark some hash marks here. So I've got 90, so halfway is 45. In fact, why don't I make this a little bit bigger? So we'll put 90 way out here, and then halfway is 45, and then 30 degrees and 60 degrees are both pretty close to the 45. And then we're going to plot some points. So if we have, so what we're trying to graph here ultimately is y equals tangent of theta. I'm going to erase this y over x because it's a different y now. And so let's plot some points. At 60 degrees, we're at 1.7. So let me mark on the y-axis here some values. So I'll just put 2 up here at the top. 1 is there in the middle. So we said at 60 degrees, we're at about 1.7. So we go to 60 degrees and we estimate 1.7 up here. And then at 45 degrees, we're at 1. So we'll plot that point. At 30 degrees, we're at 0.58. At 0 degrees, we're at 0. So apparently the graph of tangent goes to the origin. And then we have the same thing on the other side, but they're all negative now. So we'll plot the same points as we had before. And so we have 7 points in front of us. Wasn't very accurate here. Let's fix this a little bit. So negative 30, we were at 0.58. So maybe that's here. And then we're at 1. And then we're down to negative 1.7 down here. Okay, so we've got some curve that's going to hit these points, but I feel like I want a little bit more information before I really understand what the graph looks like. I can't really get much more from the unit circle per se, but let's leave the angles that we're familiar with, 35, the 30, 45, and 60, and go bigger. So what if we were at a 70-degree angle? So look at your unit circle, and now imagine a 70-degree angle on that unit circle. And we're thinking about what happened to the y and what happened to the x compared to the y and the x for the 60-degree angle. So if you go to 70 degrees, if you're starting at 60 degrees, the y is this number and the x is this number. If you go to 70 degrees, what happens to the y at that new point? It's not really a special one on a unit circle, but it's there. So hopefully we see that the y gets a little bit bigger and the x gets a little bit smaller. And so what happens to a fraction when the top gets bigger and the bottom gets smaller? What happens to the value of the whole fraction? Hopefully we see the whole fraction actually gets bigger still. Both of those changes have the effect of making the fraction bigger. So at 70 degrees, it's going to be even bigger. This tangent is going to be even bigger than the 1.7 that we got before. And then what happens at 80 degrees? So look at your unit circle. Go up to 80 degrees. It's near the top. So that's an even bigger y and an even smaller x. And so the fraction will get bigger still when you're at 80 degrees. And if you keep playing this game, it kind of makes sense because we know that the tangent of theta is the slope of that line. And as you imagine rotating that line so that it gets more and more vertical, more and more towards the 90-degree angle, you see the slope gets bigger and bigger and bigger. And so without being too precise in terms of plotting more points, if you're at 70 degrees, your tangent is bigger. If you're at 80 degrees, your tangent is bigger. And we can hopefully see that this thing will go up to infinity. The slopes go infinitely big. And so trying to draw a sketch of this infinitely big thing, it's hitting the origin and it's growing, growing, growing. And we're actually going to have a vertical asymptote right there at 90 degrees. And then in the fourth quadrant, we'll have another vertical asymptote. It's going to be decreasing, decreasing, decreasing. You can think of it in terms of the y over x, and it's the same phenomenon. The y over x is getting bigger, but the y values are all negative down there in the fourth quadrant. So it's going to minus infinity. Or you can think of the slopes of lines. And those slopes down in the fourth quadrant, those lines all have negative slope, and they're getting steeper and steeper. So this is what the graph of tangent looks like. And it turns out that once you get past 90 degrees, you just repeat. And so the graph would come over here. I'll erase this in a second. But it's just going to go from 90 degrees up to 270 degrees. Right there in the middle at 180 is where it hits the x-axis. So it just repeats every 180 degrees. Okay, so let's look at a prettier version of the graph of tangent on this GSP file. So here it is. So just to remind you, we've looked at this GSP file together before. The sine of an angle we know is the y-coordinate. So I'm going to hit the show sine button and we're going to see this vertical line pop up. And it's just translated right over here. And when we rotated, when we change the angle, you can see that vertical line gets bigger and it's copied over here. And we traced the top point and we saw our very familiar looking sine graph. So it turns out that there is a visual way to think about the tangent. I'm going to hide this guy and I'm going to click this button that says show tangent. So I'm not going to get into why it's true, but it turns out that the length of this green line segment right here is exactly the tangent of that angle. Let's make this a little bit bigger. You can see the green line segment gets big. What is the green line segment defined to be? Well, you take your line from your angle and you just extend it forever past the circle. And then you go out here to the point 1, 0 and you draw a line straight up. And wherever that extended line forever hits this straight up line forever, you put a dot right there at the intersection. And this line segment, apparently, the length of it is equal to tangent of theta. So again, I'm not going to explain why that's true. You might try to think about why that's true. I don't think it's self-evident, but it's true nevertheless. And so let's go ahead and trace this thing. Trace this point right here. And we should see the graph of tangent theta. So it hits the origin, which is the far left point right over here. And as we rotate around, that green line gets more and more vertical, bigger, 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 and we're seeing part of the tangent graph that we just drew. And then that green line is going to now flip down to minus infinity. Again, I haven't talked about what's going on really with that green line, but this is the next branch of the tangent function. It hits right there 180 degrees. That's what we said. And then it continues up, and at 270 is the next vertical asymptote. And then we get another negative branch. And then we hit the x-axis again at 360 degrees. So there's the graph of tangent. Okay, next thing to do here is talk about some of the properties of the graph of tangent theta. So let's think about the domain. This is more complicated than the domain of sine or cosine, which was all real numbers. So the domain of tangent exists almost everywhere, but it doesn't exist at the vertical asymptotes. So we'll say it's the set of all theta such that theta is not equal to, and now we need a fancy way to figure out exactly where the vertical asymptotes are. So let's just write down what one vertical asymptote, where one of them was. So we saw up above that one vertical asymptote was at 90 degrees. And then to get to the next vertical asymptote, you have to go 180 degrees away. I'll show you again this picture. Well, I guess I've already erased it, but the next asymptote after this guy was out there at 270, which is 180 degrees away. So we'll say you add 180, but you could add 180 as many times as you want. And so 180n is our way of saying just add any multiple of 180. So as long as you are not equal to 90 plus a multiple of 180, then you are in the domain of tangent. And n is allowed to be negative, which means you can subtract 180 as well. Okay, the range of tangent, let's see it. It went all the way down to minus infinity and got all the way up to positive infinity and hit every number in between. So the range is all real numbers, which you could also write in interval notation, or you could write in fancy math script, all real numbers. Okay, what kind of symmetry does the graph of tangent have? Well, let's come back up here. The standard choices for symmetry are symmetric over the x-axis, the y-axis, or the origin. So hopefully we can see that this graph is not symmetric with respect to the y-axis, because if it were, it would have to continue over there, right? This piece would need to get mirrored over there. It's also not symmetric with respect to the x-axis, because this piece would have to get mirrored down here. But it is symmetric over the origin. You pick a point, you go to the origin, keep going the same distance, and you'll find a corresponding point. This point right here, through the origin, has a counterpart way down there. So the graph of tangent is symmetric with respect to the origin. Okay, the period of the graph is how long it takes horizontally for this graph to repeat. We said that this graph repeats every 180 degrees. So the period is 180 degrees. Or in terms of radians, what is that? Pi radians. And in fact, why don't we write the radian version of the domain? So I'll just put it up here. All the theta is such that theta is not equal to, okay, what is 90 degrees in radians? It's pi over 2 plus what is 180 degrees in radians? Just pi, and then times some arbitrary integer n. So either one of these is the domain. Okay, asymptotes. So the vertical asymptotes we've seen occur at every, let's see, so we had one occurring at x equals 90 degrees, and then they just repeat every 180 degrees. So I'm just going to go ahead and use that same thing we wrote up above, 180n plus the 90. And horizontal asymptotes, there are none. No horizontal asymptotes. Midline. Okay, so does it make sense to talk about a midline, a vertical middle for something that goes up to infinity and down to minus infinity? Well, I don't know. If it does, I guess you would probably say the x-axis is the midline. I'm content saying that. And then the amplitude, okay, this one doesn't really make sense. Amplitude is how far from the middle to the top, but there is no top. So if you want to say none, that's okay. If you really like drawing the infinity symbol, you can say that too. Number 12. Right are the graphs of our three trig functions, sine, cosine, tangent. Let's identify which is which and point out some nice relationships between zeros and asymptotes of these functions. Okay, so which one is which? Well, we've just seen tangent, so I guess that must be this one that's going up to infinity. That's pretty easy to tell. And in terms of the other two, they look quite similar. There's that one and there's that one. But for me, it's always about how the thing starts. So this guy right here starts at 1, that starts at the top, so I know that's my friend cosine. And then the one that starts in the middle, which is this guy, but I'll draw and mark it over here. This guy must be sine. Okay, so I said there was something going on here with asymptotes and intercepts. So let's take a look at the zeros or x-intercepts of, which one do we want to start with? Let's take a look at the zeros or x-intercepts of cosine. Okay, so we're just going to mark these in purple. Places where the cosine hits the x-axis. So it hits right there at pi over 2, and it hits right over here at 3 pi over 2. Now what's going on with the tangent function at those 2 points? At pi over 2, what's happening with the tangent function? Well, the tangent function has an asymptote there. It's not defined there. So I'm going to draw a vertical asymptote right through pi over 2. And look over here at 3 pi over 2, there's another vertical asymptote. And so the zeros or x-intercepts of cosine happen to correspond to the vertical asymptotes of y equals tangent. And hopefully that makes sense, actually, because we remember that one of the ways to think about tangent theta was as sine theta over cosine theta. And so I'll ask you, when do we get vertical asymptotes of a graph? Does it have to do with the numerator or denominator? We know that vertical asymptotes happen when the bottom, the denominator, is equal to 0. So whenever cosine theta is 0, this thing will be undefined and this thing will have a vertical asymptote. And that's exactly what we observed. Anytime cosine is 0, you're going to have a vertical asymptote for tangent. Tangent is not defined there. Next thing I want to do is take a look at the zeros of sine. So we'll mark these here in green. So zeros of the sine function. So sine starts there at the origin, then it hits 0 over here at pi, then it hits 0 again at 2 pi. And I will ask you, what is tangent doing at those 3 points? Well, at the origin, tangent happens to hit the origin. So it's 0 right there. What about tangent at pi? Well, it crosses the x-axis right there. And how about tangent at 2 pi? Well, it crosses the x-axis there as well. And so zeros of y equals sine theta correspond to zeros of y equals tan theta. Zeros and x-intercepts are interchangeable for me. Anytime I'm saying 0, I'm talking about the x-intercept. Okay, and hopefully that makes sense, because again, if I give you a fraction and I say, when is a fraction 0, does it have to do with the top or the bottom? You should say it's the top. Fraction is equal to 0 only when the top is equal to 0. So this whole fraction is 0 anytime sine is 0. So tangent is 0 anytime sine is 0. And that's exactly what we saw at those 3 x-intercepts. They're not just x-intercepts of the sine function, they're x-intercepts of tangent as well. So some nice relationships between sine, cosine, and tangent in terms of their graphs. Okay, next page, 14. We have defined 3 ratios involving sides of a right triangle. Fill them in below. Okay, so sine theta, we've already written. I think we wrote this today, did we? Maybe we didn't. X, Y's, and R's. What is sine theta defined to be? It is y divided by r. Cosine theta is x divided by r. And tangent theta, that's our new one for today, is y over x. 15, here are the three other ratios we could talk about. They each have a name. Okay, so new functions now. Cosecant, which is abbreviated CSC of theta, turns out is the reciprocal of sine theta, which we have just up above. So sine is y over r, cosecant must be r over y. Secant, new function, abbreviated SEC, is just the reciprocal of the cosine function. So secant theta, looking up above, must just be r divided by x. Just flip over the cosine function. And then cotangent, new function, abbreviated COT. Cotan theta is the reciprocal of tan theta. So looking up above and flipping it, you see that cotan is x over y. 16. These three new trig functions complete our list of 6 trig functions in total. And I say our list, but I should say the world's list. There are exactly 6 trig functions, and we have now seen all 6 of them. They each have graphs. I'll show you the graph of y equals secant theta on Sketchpad. We're not going to worry too much about the graphs of these 3 functions here, but we'll just take a quick peek at one of them. So secant theta, I'm going to click this button and this button. And it turns out that the secant of the angle is exactly the length of this line right here. So what is that line? Well, that line is just the standard line, that the ray from with the angle of theta makes. Just extend that line forever. So imagine that line going forever. And just like before, we draw a vertical line at 1, 0 and extend it forever. And wherever those two forever lines meet, put a dot there. And the distance or the length of this line segment from the origin to that dot turns out is the secant of this angle theta. And so as you change the angle, so we make the angle a little bit bigger, angle got bigger, that blue thing got bigger, it's getting traced over here, so let's actually go back and bring it to the 0 angle. In fact, why don't we move up just a little bit here so we can see some more. Okay, so we can trace out, and what do you expect is going to happen at 90 degrees? Well, it seems like that's just like tangent, so it's probably going to be another vertical asymptote at 90. And then just like tangent, it flips over. But here it doesn't look like tangent at all. And then another vertical asymptote at 270, just like tangent had. And then this guy comes in here. So there's part of the graph of secant theta. And this graph would have continued over here to the left. And it would continue over here to the right. And ultimately, you get this kind of alternating string of cups, like cups that would hold water. So there's an up cup, and there's a down cup, and the next one is up. And it just goes back and forth. And it repeats every 360 degrees. So that's the period of this guy. And the graph of cosecant looks almost exactly the same as this one. It's just shifted a little bit horizontally, but cosecant is, again, alternating cups. Okay, coming back here to 17. There are quite a few relationships between the trig functions, and we will study many of these this semester. You'll find a bunch of these on the 6 trig functions reference sheet, which is on Moodle. Here are a few more, known as the Pythagorean identities. So we're going to write these 3 down. These are important ones. They've got a name. So Pythagorean identities. Here's the main one. So the main one says that sine squared theta plus cosine squared theta is equal to, and then I'm going to leave the magical answer here blank for a second. First, let's make sure we're clear on what sine squared means. So if I were to write sine squared of, say, 38 degrees plus cosine squared of 38 degrees, what that really means, put an equal sign here, is that you find the sine of 38 degrees, and whatever answer you get, you square it. And then to that, you add whatever you get for cosine of 38, but first you got to square that one too. So this sine squared doesn't mean square 38. It means find the sine of 38 and then square the answer. Okay, so let's just see what the calculator has to say about this. So we're going to type in the sine of 38 degrees. Again, I hit one of those trig buttons, so I check my mode. Degree mode is correct. So sine of 38 is some messy number, that's fine. And then we'll go ahead and square that messy number, and we get that other messy number. And then we'll do cosine of 38. And we'll go ahead and square that. And so what I should be looking at is sine of 38 squared plus cosine 38 squared, which is the 0.379 and change, plus the 0.6209 and change. So it looks quite messy. I mean, you got two messy numbers. You're just adding them up. So what happens when you add up the 6 and the 3 here? Well, we get 9. All right, so it's 0.9. Then 7 and 2, that's also 9, so we're at 0.99. And then 9 and 0 is 9, and 0 and 9 is 9. 3 and 6 is 9. They all look like 9, except for this last one, which looks like a 10. That's kind of deceiving. It shouldn't be a 10. There's some rounding happening here. It should be a 9. So what does that mean? It's 0.999999. That's really close to a nice number. So how about we type this in one shot? So we'll do sine of 38 squared plus cosine of 38 squared. Nope, parentheses, squared. And the 0.99999 is actually 1, exactly 1, not a little less than 1, but really 1. So it turns out that this thing here is equal to 1. And in general, no matter what angle you have, sine squared theta plus cosine squared theta is 1 all the time. So that right there is one of our Pythagorean identities. It's kind of surprising. Okay, there are two other Pythagorean identities. I can never remember them, but I can figure out how to derive them, and maybe you can too. You're going to take the identity that you started with. I'll just copy it again down here. And you're going to divide both sides by sine squared. So we're going to divide everything over here by sine squared theta, and better do the same thing on the right-hand side. And then on the left-hand side, we're going to split this up into two fractions. We're going to say this is really sine squared plus cosine squared, each of them divided by its own copy of sine squared. And then over here, I'll just rewrite it, 1 over sine squared. Okay, so hopefully that's that rule about adding fractions is familiar, so this should be legitimate. And then we're going to start cleaning this up. So what is sine squared over sine squared? Well, that's easy. That's just 1 plus. Okay, cosine squared over sine squared. All right, temporarily ignore the squares. Just cosine over sine. Okay, cosine over sine we haven't seen before, but we have seen its reciprocal before. Again, forgetting the squares. But if you flip this over and look at it as sine over cosine, that's another trig function. Which one of the 6 trig functions is exactly sine over cosine? It's tangent. It's the one we introduced today. But this is upside down. This is cosine over sine. Well, wait a minute. If you're telling me upside down tangent, we actually gave a name to that. We saw that the tangent function has an upside down partner, and that partner is the cotangent function. So that means that this cosine over sine business, still ignoring the squared, is really equal to cotangent. But each of them is squared. And so if you take a moment to write out the details a little bit, you should be able to convince yourself that cosine squared over sine squared is really the same as cotan squared. Equals 1 over sine squared. Okay, same thing as before. Ignore the squared for the moment. 1 over sine, that's one of our trig functions. Which one of the trig functions is the reciprocal of sine? We saw it up above. It's cosecant. So this is cosecant theta. There's actually 2 copies of it because the sine was squared. So again, hopefully you can convince yourself that the right-hand side is just cosecant squared theta. Okay, so we've now got 2 of our Pythagorean identities. There's this one here, and there's the main one up here. Well, those are 2 of the 3 Pythagorean identities. So what I'm going to ask you to do is see if you can derive the 3rd Pythagorean identity. You're going to do that by copying this first one. So sine squared plus cosine squared equals 1 should go here. And then we decided to divide by sine squared, but just as well we could have divided by cosine squared. So what you're going to do on this brand new copy you have over here is divide both sides by cosine squared and see if you can follow the same kind of thing that we did here. Pause the video and come back when you have a brand new identity. It should look something like that one. Okay, so if we're back and we did the work, hopefully we got this identity, tan squared theta plus 1 is equal to secant squared theta. So I'll highlight that one. That is the third and final Pythagorean identity. So 3 equations that are true all the time, kind of surprising. We'll spend plenty of time thinking about those equations later on the semester, but they are quite important and useful. Okay, next page, number 18. If we know the value of one of the trig functions at some angle, we can use our identities to find the values of the other 5 trig functions. For example, suppose that theta is in the 4th quadrant and cosine theta is 12/13. Let's find the values of the other 5 trig functions at theta. We'll do this in a couple of different ways. Okay, so in this example, we're just kind of playing detective. We have some angle theta. Apparently it's in the 4th quadrant. So I'm going to draw this here and say, okay, theta is that angle someplace in the 4th quadrant. I have no idea exactly where in the 4th quadrant. And then I'm told that cosine of theta is 12/13. Okay, so what I'm going to do is start filling in the blanks over here, or at least get a template going. So it says find the values of the other 5 trig functions. So I'm just going to do all 6 of them, just to be complete. So our goal is to figure out what each of these things is. And if you line it up right, then as soon as you have the main 3 trig functions, then you can get the other 3 by just flipping them over. But I'll test you right now. Which one is the one that corresponds to sine? Which one is the reciprocal of sine? Hopefully we see that that is cosecant. Secant goes with cosine, cotangent goes with tangent. Okay, so we'll fill in the first one, the one that's given to us is 12/13. That's easy. And now what we're trying to do is figure the values of sine and tangent. And so we have to be little detectives here and take the tiny bit of information we're given and somehow get all that we need in order to figure out what sine of theta is and what tangent of theta is. Okay, so there's 2 different ways to do this. Let's start with finding sine. So let's use one of our brand spanking new identities. Sine squared plus cosine squared theta is always, always, always 1. Doesn't matter whether theta is in radians or degrees, this identity is true. Well, both thetas have to be measured in the same thing, so both in degrees or both in radians, and then it's true. Okay, so let's fill in a blank here. I don't know what sine of theta is, but I do know that cosine of theta is 12/13. And I know that cosine of theta is supposed to be squared. So apparently that 12/13 is supposed to be squared. So that's just substituting. And let's clean this fraction up a little bit. So this is 144 over 169. Go ahead and subtract that fraction from both sides. Get a common denominator and do the subtraction, and hopefully you see that it's 25 over 169. And so that's what sine squared theta is, but I don't want that squared in there. I just wanted sine theta. So to get rid of the square, we'll take the square root of both sides. So we say sine theta is equal to the square root of 25 over 169. But the square root of 25 over 169 simplifies, in this case, to 5/13. So that's it. That's our answer. Sine of theta is 5/13. Done. Okay, so let's, there's a mistake in there. So if you're worried about the mistake, then we'll get to it. So hold your horses. But let's assume that we didn't know there was a mistake there. And we're just going to do the same kind of thing in a different way. So let's take a look at our picture and say, okay, theta was this angle that was in the 4th quadrant. Well, I wrote theta as being this kind of big angle, but just as well, we could have said theta was this small negative angle. Just go the clockwise direction. So it's some negative angle. That's okay. But if you know that cosine is 12/13, then you know something about a right triangle that we're going to draw. You know that cosine is always the x divided by the r. So apparently there's some right triangle that I can draw where the x is 12 and the r is 13. So how about we just go ahead and arbitrarily draw a right triangle any place out here, makes no difference where. And then we're going to start filling in. We know that the x is 12. So the x coordinate, so we're looking at this point right here. The x coordinate is 12, so 12 must be the length of this line. The y value I don't know yet. I'll color that in purple, so that's some unknown y. And then the r value we'll make green, so that's this hypotenuse thing here, but the r is 13 from what was given to us. So we can fill this in and say that's equal to 13. Okay, fair enough. So then we're going to look at that right triangle and try to figure out what y is. So what famous theorem can we use to solve for y in that right triangle? Okay, so hopefully we see that we can use the Pythagorean theorem. Let's use that here. Pythagorean theorem. We know the equation is a squared plus b squared is c squared. Just have to make sure the c is the hypotenuse, so let's get that one in there first. That's the 13. The a and the b makes no difference which one is which, so actually I'm going to put the b. I'm going to leave the a as a, and I'm going to make the b 12. So we get this equation. And then we'll do some arithmetic here. So that's 144, that's 169. Those numbers look familiar to me. And then we'll subtract the 144, and we get 25. And then we'll take the square root of 25, which happens to clean up in this case to 5. And that 5 also looks familiar. So then in terms of this picture, so a is 5, and I guess what we were saying was that a was the y value here. So this is equal to 5. Super. And that 5 is the same 5 that we found over here. So in terms of figuring out what sine of theta is, well, we know the XYR definition of sine theta is y over r. So the y value we just found was 5. The r value was given, it's the green 13, and we get, lo and behold, 5/13. Again, exactly the same as we got before. Okay, so two things. Number one, we call this guy right here the Pythagorean identity because it's pretty much that same equation, right? A squared plus b squared is c squared. Sine squared plus cosine squared is 1 squared if you feel like it. So that's why we call the Pythagorean identity, because it is essentially the Pythagorean theorem. But here's the problem. The problem is we got it wrong. In this picture, I, without doing any work, can tell you that the y coordinate at this point right here is something negative. It's x and then negative something because it's down below. It's in the fourth quadrant. So that y must have been negative. So if you're going to tell me anything, I guess you'd have to tell me that it's -5, not +5. So where did we go wrong? Well, right here. When we took the square root of both sides, we forgot to do something. Or at least I forgot. Maybe you didn't forget. But I forgot to put in that plus or minus. It's really easy to do. So over here where we had 5, we really should have had plus or minus 5. And remember how I said we were little detectives? We need to be detectives and know that there's this plus or minus that we have to choose the right one. How do you know which one is right? You look at the picture. The y value here at this point is definitely positive because it's in the fourth quadrant. So it must have been -5, which means that over here, that should have been -5. And that's how we would fix it with the Pythagorean theorem. Same thing went wrong when we used the Pythagorean identity. Right here, what did we do to both sides? We took a square root. I forgot, hopefully you didn't. Plus or minus there, plus or minus there. I'm putting it as if it's on top, but really it's just in the front of the fraction. And again, it is your job to have a decent picture in front of you and to know that there's this opportunity to pick either the plus or the minus. We have to pick the minus because this is a fourth quadrant angle. Okay, and once we've got that, finding tangent should be pretty straightforward. So we know that tangent in terms of x, y's, and r's is y divided by x. And the y looking at the picture in purple is -5. The x looking at the picture in red is 12. So that's what goes for tangent theta, is -5/12. And that's the hard work. Easy work, if you've lined it up right, is to just flip over each of those numbers. So cosecant is the reciprocal of sine, so negative 13 over 5. And secant is positive 13 over 12. And then cotan is negative 12/5. Okay, so the activity follows, and the activity will give you plenty of practice with doing this kind of detective work that we did up here. So give the activity a decent shot on your own before looking for the video for the activity on YouTube.